In March 2023, a Samsung semiconductor engineer pasted proprietary source code directly into ChatGPT to ask for a bug fix. Within weeks, Samsung confirmed the incident internally. Confidential chip design data had been transmitted to an external server, processed by a model whose training pipeline they had zero visibility into. This was not a phishing attack. This was not a rogue employee circumventing policy. This was the intended use case of a cloud LLM API, working exactly as designed. And that is precisely what makes so dangerous. The engineer did nothing wrong by the standards of everyday productivity tools. But the moment that API call left the corporate perimeter, the data governance contract your legal team spent months negotiating became effectively irrelevant. Ask yourself, how many of your developers made a similar API call this morning? By the end of this lecture, you will have a structured framework to answer that question and know exactly what architectural decision to make next. So how did this happen contractually? Let us look at the mechanism. When your team signs up for a major cloud LLM provider, whether it is OpenAI, Google Gemini, or Anthropic, there is a data retention and model improvement clause buried in the terms of service. For consumer tier and many developer tier API plans, your prompt inputs may be retained for up to 30 days for abuse monitoring. More critically, unless you explicitly opt out, and in many legacy plan versions, opt-out was not even available, your data could be used to fine-tune future model versions. This is not speculation. OpenAI's March 2023 TOS explicitly stated that API inputs could be used to improve model performance, unless the user submitted a specific opt-out form. Most enterprise teams never read past the pricing page. Here is the structural problem. Even when opt-out exists, the burden of proof that your data was not used lies entirely with you, not the vendor. Under GDPR Article 5 and Korea's Personal Information Protection Act, that asymmetry creates direct regulatory liability for your organization. The contractual mechanism is not a bug, it is the business model. And in the next section, I will show you the 4 decision axes that let you systematically evaluate whether your organization can afford to accept that model. Now that we have established the threat vector, let me show you exactly what you will be equipped to decide by the time this lecture ends. Enterprise architects and CTOs face a recurring failure mode when evaluating cloud AI versus local LLM deployment. They optimize on a single axis, usually cost or developer experience, and ignore the full decision surface. I have structured this lecture around 4 axes that, taken together, give you a complete picture. First, total ownership, not just API pricing, GPU amortization, inference latency, SLAs, and model maintenance overhead. Second, data governance. Where does your data reside? Who can access it? And can you demonstrate control to an auditor? Third, regulatory compliance. This is non-negotiable for financial institutions under FSS guidelines, healthcare under HIPAA, and any organization processing personal data under Korea's PIPA or the EU's GDPR. Fourth, operational complexity. What does your team actually have the capacity to run and maintain at scale? These 4 axes form a decision matrix. Each one creates a different forcing function toward cloud or local deployment. And the key insight, which most vendor white papers deliberately obscure, is that optimizing for one axis without modeling the others creates architectural debt that compounds over time. Let us map this out clearly before we go further. Here is the concrete deliverable this lecture is built around. By the time we reach Chapter 6, you will have completed an architecture decision record, an ADR, that you can present directly to your CTO, your security team, or your compliance officer. An ADR is not a theoretical exercise. It is the standard output format used by enterprise architects at organizations ranging from Netflix to major Korean financial institutions to document why a specific architectural choice was made, what alternatives were considered, and what the accepted trade-offs are. The ADR template we will build together covers all 4 decision axes: your TCO model with cloud and local cost projections side by side, your data governance assessment mapped against your actual regulatory obligations, your operational readiness score, and your vendor lock-in exit strategy. This is the document that separates an architect who says we should probably consider local LLM from one who walks into the boardroom and says, here is the structured analysis, here are the 3 options, and here is my recommendation with the risk profile for each. That second architect is who this lecture is designed to create. In the next chapter, we will begin building the analytical foundation, a precise taxonomy of cloud AI dependency risks that most organizations only discover after they are already locked in. The patterns are more systematic than you expect, and they start the moment you make your first API call. Before we talk about solutions, we need to be precise about the problem. When your application sends a prompt to a cloud LLM API, that text travels across the public internet. Encrypted, yes, But encryption only protects data in transit. The moment your prompt arrives at the vendor's inference endpoint, it is decrypted, processed, and in many default configurations, logged for model improvement. This is not a hypothetical threat. This is the documented default behavior of multiple major platforms. Think about what actually lives inside your enterprise prompts. Customer names, account numbers, internal product roadmaps, legal documents fed into summarization pipelines. Every one of those tokens is now resident on infrastructure you do not control, governed by a data retention policy you did not write, and subject to jurisdictions you may not have mapped. TLS encryption is a transport layer guarantee. It says nothing about what the vendor does with your data after decryption. Enterprise architects who conflate transport security with data sovereignty are making a category error that regulators are increasingly penalizing. The 4 risk vectors we will map today: data leakage, cost volatility, service continuity, and vendor lock-in, each operate independently, which means they can compound simultaneously. But here is the part most vendor sales decks never show you. The data leakage vector is the only one that cannot be fixed with money after the fact. Now let us talk about money. Specifically, why cloud LLM pricing is structurally hostile to enterprise budget planning. When GPT-3 3.0 launched, the pricing was set at a level that made proof-of-concept economics look attractive. Then came the model updates, context expansions, and gradual price adjustments, some up, some down, but always on the vendor's timeline, not yours. Here is the critical insight for enterprise architects. The price changes you see on the public pricing page are not the whole story. The real cost volatility comes from 3 compounding factors. First, your token consumption grows non-linearly as you context, history, and retrieval-augmented generation to your pipelines. Second, model upgrades often change the token per task ratio. A task that required 500 tokens last year may require 1,100 tokens today because the model generates more verbose reasoning. Third, and most destructive to budget models, the vendor can deprecate the model version you optimized for, forcing migration to a newer, more expensive model on their schedule. I have personally reviewed enterprise cloud AI budgets that were off by a factor of 4 versus initial projections, not because of fraud or mismanagement, but because the token cost model is genuinely difficult to forecast. This unpredictability alone is sufficient reason for CFOs to demand a cloud versus local cost analysis. And the timeline you are about to see makes that case more powerfully than any consultant's slide deck. Data leakage and cost volatility are risks you can partially manage with contracts and budget reserves. Service continuity risk is different. It is a binary event. Your production system either works or it does not. And when it does not, the root cause is in infrastructure you do not own. Let us look at the documented record. Major cloud LLM providers have experienced service outages ranging from minutes to hours, affecting production systems across industries. More strategically damaging than outages, however, are deprecation events. When a vendor announces end of life for a specific model version, typically with 90 to 180 days notice. For an enterprise that has built prompt engineering, fine-tuning workflows, and downstream integrations around a specific model version, 90 days is not adequate remediation time. The table you are looking at now catalogs actual disruption events, their duration, and critically, the operational blast radius. Notice the pattern. Outages cluster around major model releases and infrastructure migrations. Precisely the moments when vendors are most focused on new capabilities and least focused on backward compatibility. From a business continuity planning perspective, ISO 22301 requires organizations to identify single points of failure and quantify their recovery time objectives. Any production system with a single cloud LLM dependency and no fallback architecture, by definition, a single point of failure. The question is not whether a disruption will occur. The historical record answers that. The question is whether your architecture can survive it. And that question leads directly into the vendor lock-in analysis we are about to conduct. The 3 risk vectors we just examined, data leakage, volatility, and service continuity, are operational risks. Regulatory risk is categorically different. Operational risks create costs and delays. Regulatory violations create legal liability, institutional penalties, and in some cases, personal liability for executives and data protection officers. Let us be precise about the legal architecture. Korea's Personal Information Protection Act, PIPA, establishes hard constraints on the cross-border transfer of personal data. Article 28-8 requires that before transferring personal information abroad, the data subject must be notified of the recipient country, the recipient's identity, the purpose of transfer, and the retention period. For a cloud LLM workflow processing, any form of customer data, names, behavioral data, financial records, Each API call that includes that data is a cross-border transfer requiring either explicit consent or a compliant transfer mechanism. Now consider what this means in practice. Your customer service chatbot, fed on customer interaction history, is generating a cross-border transfer event with every inference call. Your HR system, using an LLM screen rescreens containing employee personal data, is doing the same. The compliance team often discovers this only after the architecture is in production, and at that point, remediation requires either a full data anonymization layer, a fundamental rearchitecture, or switching to domestic or local inference endpoint. The law does not care that TLS was in use. The law asks where the data was processed and by whom. That question has a definitive answer for every cloud LLM API call, and that answer is almost never inside your compliance boundary. If PIPO creates a legal barrier for enterprises handling personal data broadly, the Financial Services Commission and Financial Supervisory Service Guidelines create an even more specific and immediate barrier for the financial sector. The FSSS Cloud Computing Use Guidelines, established under the Electronic Financial Transactions Act, create a tiered system for classifying financial data and specifying which tiers may be processed on which types of cloud infrastructure. Core financial data, defined to include transaction records, credit information, and account data, faces strict requirements around data localization, audit access, and incident response that are structurally incompatible with standard cloud LLM API terms of service. Think about what this means for a Korean commercial bank that wants to deploy an AI assistant for loan officers. The loan officer's queries will naturally include borrower information. The LLM needs that context to be useful, but routing that context through an external cloud LLM API is precisely what the SS guidelines restrict. This is not a gray area. The checklist you see now represents the actual compliance gates that financial institutions must clear before deploying any AI system touching regulated data. Walk through each item and ask yourself, which of these can a standard cloud LLM API vendor satisfy by contract alone, without architectural changes on your side? The answer fundamentally shapes your infrastructure decision, and the same pattern repeats healthcare, defense, and public sector, each with their own sector-specific overlay on top of the baseline PIPA requirements. Some enterprise architects hearing PIPA and FSS compliance requirements for the first time think, this is a local Korean regulatory peculiarity, a traditional constraint that will relax as cloud AI becomes normalized. That interpretation is strategically dangerous and factually wrong. The global regulatory direction is toward more restriction, not less. GDPR Article 44 through 49 has created the same cross-border transfer framework in Europe, and the GDPR enforcement record shows regulators are increasingly applying it to AI processing. The EU AI Act, now in force, adds a systemic risk classification layer specifically targeting high-capability foundation models, which means the very models most enterprises want to use face the highest regulatory scrutiny. The pattern is clear. Data sovereignty requirements, cross-border transfer restrictions, and AI-specific risk frameworks are converging globally. What Korea requires today, the combined GDPR plus AI Act framework, is moving toward for European enterprises. What the FSS requires for financial data today, global financial regulators, including the Basel Committee, are signaling for international banking. This means the compliance architecture decision you make today, cloud versus local, is not a decision for this year's regulatory environment. It is a decision for the regulatory environment of 27 and beyond. Organizations that build low inference capacity now, for compliance reasons, will find themselves ahead of the curve. Organizations that build cloud LLM dependency now and plan to comply later will face a far more expensive re-architecture under time pressure. The regulatory wind is not at cloud's back. And now, let us turn to the dimension that compounds every one of these risks: vendor lock-in. We have covered data risk, cost volatility, service continuity, and regulatory exposure. Each of these is serious in isolation, but vendor lock-in is the mechanism that transforms each individual risk into a structural trap. Because lock-in is what makes it expensive to respond when any of the other risks materialize. Before we can quantify the switching cost, we need to be precise about what lock-in means in the LLM context. It is not one thing, it is three distinct and stackable dependency layers, and most enterprises only recognize the first layer until they try to migrate. The first layer is API lock-in. Your code has direct dependencies on a specific SDK and endpoint structure. This is the layer that vendor portability promises address, and it is actually the easiest to solve. The second layer is prompt format lock-in. The specific instruction patterns, few-shot examples, chain-of-thought structures, and system prompt architectures you have engineered are optimized for one model's behavior. A prompt that performs at 95% accuracy on GPT-4 may perform at 6% on a different model, including open-weight models with similar benchmark scores. This layer is often invisible until migration begins. The third and most expensive layer is fine-tuned model lock-in. If you have performed supervised fine-tuning or instruction tuning on a vendor's proprietary base model, that training investment is entirely non-transferable. You cannot export the weights. You cannot continue training on a different platform. You start over. Understanding these three layers is the prerequisite for understanding why the switching cost analysis you are about to see consistently surprises enterprise decision makers. Theory becomes decision relevant when it is attached to a number. Let me walk you through a worked example that I have constructed from patterns across multiple enterprise migration assessments. The scenario: a mid-size financial services firm has been running a proprietary cloud LLM deployment for 18 months. They have built 5 production use cases: document summarization, contract review, customer inquiry routing, report generation, an internal knowledge base queue, and the A system. They want to migrate to a locally deployed, open-weight model for the compliance and cost reasons we have just discussed. When the project scope is estimated, the Layer 1 costs, API abstraction endpoint reconfiguration, come in at roughly what everyone expected: manageable. Then the Layer 2 costs arrive. For each of the 5 use cases, the prompt engineering work that took weeks the first time now requires a full regression testing cycle, plural optimization. Because the new model's behavior profile is different even if benchmark scores are similar, the accuracy delta on contract review, the highest stakes use case, requires 3 full re-engineering iterations before reaching acceptable performance. And if Layer 3 applies, if any fine-tuning was performed, the cost multiplies again. The table you are seeing now breaks this down as a migration cost matrix. Pay particular attention to the rightmost column, the ratio of migration cost to original implementation cost. In every category, migration costs more than the original build. This is the architecture tax of lock-in, and it is a tax that was never included in the original cloud LLM business case. We have now built a complete taxonomy of cloud LLM risk. Let me consolidate it into the risk classification framework that enterprise architecture review boards actually use. When we plot all 4 risk vectors on a standard likelihood impact matrix, the same 2x2 format familiar from NIST Risk Management Framework and ISO 30000, a clear pattern emerges. Data leakage and regulatory non-compliance sit in the high likelihood, high impact quadrant for any organization processing regulated or sensitive data. Vendor lock-in sits in the medium likelihood but very high impact quadrant, because while you may not encounter a forced migration tomorrow, when it happens, it is an enterprise-level program. Cost volatility is high likelihood but variable in impact depending on your scale and contract structure. Service continuity risk is lower likelihood but, for real-time production systems, can be catastrophic errors. The critical insight from this matrix is that these risks are not independent. A model deprecation event simultaneously triggers the lock-in risk, forcing migration, the cost volatility risk, minimal pricing, and the service continuity risk if the migration is not completed before end of life. They cascade. This risk compounding is what makes cloud LLM dependency fundamentally different from other cloud service dependencies. A cloud database going down costs you uptime. A cloud LLM going away or changing behavior costs you uptime, plus compliance exposure, plus migration investment, all at the same time. Now that we understand what we are defending against, the question comes: what architecture options actually provide a credible alternative? That is exactly what Chapter 3 answers. And the options available today are more mature and more accessible than most organizations realize. In the previous chapter, we cataloged the hidden risks of cloud AI dependency, data residency violations, unpredictable pricing, and the silent API deprecation that can cripple your production system overnight. Now the natural question becomes, what is the alternative, and is it actually enterprise-ready? Let's start with the most fundamental prerequisite. Before you can talk about local deployment, you must understand the distinction between open source and open weight models. Open source means the training code, data pipelines, and model weights are all publicly available. Open weight means only the trained weights are released. You can run inference and fine-tune, but you cannot audit how the model was built. For enterprise data sovereignty purposes, this distinction is actually secondary. What matters is weight ownership, your right to download, store, and serve the model weights on your own infrastructure without a runtime license or an API call going outbound. Models like Meta's Threes, Mistral, and Alibaba's Qwen give you exactly that. They are the foundational prerequisite for true data sovereignty, because once the weights are on your server, your data never needs to leave your network perimeter. But here is the trap many architects fall into. confusing model availability with deployment readiness. Weight ownership is necessary, but it is not sufficient. And that gap is exactly what we will close in this chapter. Now, weight ownership solves the legal and governance problem, but it immediately creates an engineering problem. A raw 70 billion parameter model in full float 32 precision requires approximately 280 gigabytes of GPU VRAM. That is 4 or 800 gigabytes cards just to load the model. For most enterprises, that infrastructure cost is a non-starter. This is where quantization becomes the single most important enabling technology in the local LLM story. Quantization reduces the numerical precision of model weights from 2-bit or 16-bit floating point down to 8-bit integers, 4-bit integers, or even lower. The GGF format, pioneered by the Llama-Bot PPP project, packages quantized weights in a portable, hardware-agnostic format that can be loaded on CPUs, app silicon, and consumer GPUs alike. The critical insight for enterprise architects is the performance trade-off curve. Moving from float 16 to 4-bit quantization reduces memory footprint by roughly 75%, while benchmark degradation on standard reasoning tasks is typically under 5%. That is an extraordinary engineering trade-off. A 70B model that required 140 gigabytes of VRAM at float 16 now runs in approximately 40 gigabytes, within reach of a single consumer-grade GPU. As we will see in a moment, a MacBook. The practical implication: quantization is not a quality compromise. It is an infrastructure democratization technology, and understanding it changes your hardware procurement calculus entirely. Here is the benchmark that changed the enterprise conversation in early 2025. And if you have not internalized its implications, you are likely still overestimating the cost of local AI. Apple's M4 MacBook Pro, with 128 gigabytes of unified memory, runs Llama 3 Infinity B at 4-bit quantization, a model that rivals 335 on most enterprise reasoning benchmarks, at approximately 15 to 20 tokens per second. That is a usable, interactive inference speed for document analysis, code review, contract summarization, and internal QA workflows. The hardware cost: under 1,000 per unit. Compare that to a cloud deployment at 1,000 per token for a comparable model. If a power user generates 500,000 tokens per month, which is realistic for a developer using AI-assisted coding daily, that is 1,000 per month, or 1,000 per year, per seat. The MacBook pays for itself in under 4 months, with zero data leaving the device. This is not a theoretical edge case. This is the new hardware baseline that every enterprise architect must factor into their local AI cost model. The hardware barrier to local LLM deployment has not just lowered, it has structurally collapsed, and that changes every procurement and architecture decision downstream. In the next section, we will look at which runtime you use to actually serve that model, because the runtime choice is where most enterprise deployments fail silently. Now that we have established that the model weights are portable and the hardware is accessible, the next architectural decision is the runtime. The software layer that actually loads the weights, manages memory, handles inference requests, and exposes an API surface to your application. The runtime is where architectural fit determines operational success, and choosing the wrong one for your use case is the most common mistake I see in enterprise pilots. Let's start with Llama. Llama is designed with a developer-first philosophy, and its architecture reflects that clearly. At the top layer, you have a REST API that is intentionally compatible with the OpenAI API schema, meaning any application already with GPT 3.5 or GPT-4 can switch to a local Llama instance by changing a single base URL. Below that sits the model management layer, which handles downloading, versioning, and switching between models using a Docker-like interface. Llama Pool Llama 3 is genuinely that simple. The inference engine layer uses Llama 20 CPP under the hood, giving you CPU and GPU acceleration across platforms. The bottom layer is the hardware abstraction, supporting NVIDIA CUDA, Apple Metal, and AMD ROCm. The ideal deployment context for Llama is a single developer, or a small team of 5 to 15 people running a shared local inference server. It handles 1 to 3 concurrent requests gracefully. Beyond that, you start hitting hidden queuing issues that Llama was never designed to solve. But for rapid prototyping, internal tools, and developer productivity use cases, it is the fast path from zero to a running local model. The question is, what happens when you need to scale beyond a handful of concurrent users? The second runtime in our comparison serves a complete different organizational function, and understanding that function is critical for enterprise rollout strategy. LM Studio is not primarily a production inference server. It is an enterprise pilot enablement tool, and that framing changes how you evaluate it. The top layer is a graphical desktop application. a model hub browser where users can search, download, and switch between hundreds of models without touching a command line. This matters enormously in enterprise contexts where your primary stakeholders are legal teams reviewing contracts, HR teams drafting policies, or compliance officers doing regulatory analysis. These users cannot install Python environments or write API calls. LM Studio gives them a ChatGPT-like chat interface running entirely locally, and that visual familiarity dramatically reduces change management friction during pilot programs. Below the GUI sits a local inference server that can expose an OpenAI-compatible API, making it possible for developers to connect applications to it when needed. The model management layer pulls from Hugging Face and supports GGF format natively. The hardware layer supports Metal and CUDA, but with less performance tuning than Ollama or VLLM. Here is the strategic use case. If you are running a 90-day enterprise AI pilot, and you need 10 non-technical department heads to evaluate whether local LLM meets their workflow needs, LM Studio is how you do that without a dedicated DevOps engineer in every meeting. It proves the concept to the business side. But do not make the mistake of promoting it to production serving. That is where the next runtime takes over. The third runtime is categorically different from the first two, and I want to be precise about why. Ollama and LM Studio solve the accessibility problem. VLLM solves the throughput problem. And in enterprise production environments, throughput is the only metric that ultimately matters for cost justification. VLLM was developed by researchers at UC Berkeley, and its core innovation is page detention, memory management algorithm that treats the GPU's KV cache the way an operating system treats virtual memory pages. In traditional inference, each request pre-allocates a fixed contiguous block of KV cache memory for its maximum context length, leading to significant internal fragmentation and wasted VRAM. Page detention allocates KV cache in small, non-contiguous pages, similar to real memory, allowing the system to serve dramatically more concurrent requests on the same GPU hardware. The practical result, on a single 118 GB GPU, VLLM typically achieves 2 to 4 times the throughput of naive inference implementations. Combine that with continuous batching, where new requests are dynamically inserted into ongoing batch computations rather than waiting for the current batch to complete, and you get the performance profile that enterprise deployments actually require. The infrastructure requirement is real. You need at minimum one high-end NVIDIA GPU, and production deployments typically involve multi-GPU nodes with NVLink. The operational complexity is also significantly higher. VLLM is a Python service that needs to be containerized, monitored, and scaled. But if you are serving a workforce of 500 or more users, or if you are building an internal AI platform, VLLM is the only in this comparison that belongs in your production architecture. The question now becomes, how do you choose between these three for your specific situation? Now let's synthesize. Rather than asking which runtime is best, the correct enterprise question is which runtime fits which organizational context. This comparison matrix gives you a decision instrument across 3 axes that map directly to enterprise procurement criteria. On operational complexity, which is really asking how much dedicated DevOps effort this requires, Ollama scores low, LM Studio scores the lowest, and VLLM scores high. A VLLM deployment is a Kubernetes workload. It needs monitoring, auto-scaling policies, and an MLOps team to maintain it. On throughput, measured in concurrent users and tokens per second, Ollama handles tens, LM Studio handles single-digit concurrent sessions, and VLLM handles hundreds to thousands. On infrastructure cost per unit of capacity, factoring in hardware amortization and engineering time, Ollama is the most cost-efficient for small teams. LM Studio has nearly zero marginal infrastructure cost since it runs on existing workstations, and VLLM requires meaningful GPU infrastructure investment, but delivers the lowest cost per token at scale. The enterprise decision framework maps cleanly. Start with LM Studio for business stakeholder pilots, graduate to Ollama for developer teams and internal tooling, and invest in VLLM when you have validated demand from more than 100 daily active users. This staged progression also reduces organizational risk. You are not committing to GPU server infrastructure before you have proven business value. In the next section, we will look at where these runtimes live in your network architecture, because a low LLM running on the wrong network segment can be just as risky as a cloud API. Selecting a runtime is only half the architectural decision. The other half, and the one that directly determines your regulatory posture and attack surface, is deployment topology. Where in your network does the inference endpoint live, and what data flows across which boundaries? There are 3 fundamental topologies for enterprise local LLM deployment. The first is edge device deployment. The model runs directly on the end user's device, a MacBook, a workstation, or a rugged edge compute unit. The security boundary is the device itself. Data never enters the network. This is the strongest possible isolation posture and the required pattern for air-gapped environments. Think defense contractors, classified government systems, or industrial control networks, where any outbound traffic is a policy violation. The second topology is the on-premise GPU server. A centralized inference server lives inside your corporate network, typically in a DMZ or a dedicated AI services segment. Client devices send requests over the internal network, and the inference endpoint is firewalled from the public internet. This is the most common pattern for enterprises with shared AI platform ambitions. It centralizes hardware cost, simplifies model governance, and creates a single audit point for all inference traffic. The third topology is hybrid routing. A policy-based router classifies incoming prompts by data sensitivity and routes high-sensitivity queries to your on-premise server while sending low-sensitivity general queries to a cloud API. This is architecturally elegant but operationally complex. The classification logic itself becomes a critical security control, and a misclassification can silently route sensitive data to the cloud. Each topology solves different problems. The question of which one you need comes down to a single variable. And we will name that variable precisely in the next scene. Once you have selected a topology, the next engineering obligation is enforcing the data perimeter around your local inference endpoint. This is where I see enterprises make a critical assumption error. They deploy a local LLM, congratulate themselves on data sovereignty, and then fail to secure the inference itself, creating a new attack vector that did not exist before. Think about this carefully. A VLLM server running on your internal network with an unauthenticated REST API is an open prompt injection surface for any device on your network. And if your network has been compromised, which NIST S800-207, the Zero Trust Architecture standard, explicitly assumes as default threat model, that endpoint is exposed. The data perimeter enforcement process has 5 stages. First, network segmentation. The inference server lives in its own VLAN or network security group, accessible only from explicitly allow-listed source IP ranges. Second, mutual TLS authentication. All client-to-inference server traffic is encrypted in transit, and client certificates validate the requester identity. Third, API gateway layer. A dedicated API gateway enforces rate limiting, request logging, and policy-based access control before traffic reaches the model. Fourth, inference audit logging. Every prompt and completion is logged with user identity, timestamp, and token count to an immutable audit trail. This is the artifact a compliance team needs for GDPR Article 30 records of processing activities or for financial security audit requirements under Korea's ISMSSP framework. Fifth, output filtering. A post-processing layer screens model outputs for inadvertent PA or confidential data regurgitation before returning responses to clients. This is not paranoia. It is the minimum viable security architecture for a production AI endpoint, and skipping any of these 5 layers creates a gap that a compliance audit will find. Let me close this chapter with the most actionable framework I can give you, a workload sensitivity classification scheme that maps directly to topology selection. This is the decision instrument that removes ambiguity from your architecture review process. The classification has 3 tiers. Tier 1 is public or general data, information that is already in the public domain or carries no regulatory obligation, marketing copy drafts, generic code generation, summarizing publicly available documents. For Tier 1 workloads, cloud APIs are entirely acceptable. The cost efficiency and capability of frontier models, like GPT-4R or Claude 3.5 are genuine advantages. And forcing this traffic through local infrastructure wastes your hardware budget. Tier 2 is internal or business-sensitive data, employee communications, internal business processes, unreleased product information, customer data that is pseudonymized or aggregated. This is the gray zone where most enterprise AI workloads live. For Tier 2, the on-premise GPU server topology is the recommended pattern. It balances cost efficiency with data control, and it satisfies most regulatory frameworks without the operational complexity of full-edge deployment. Tier 3 is highly sensitive or regulated data. Personally identifiable information in its raw form, medical records, financial transaction data, classified information, or any data explicitly named in your data protection agreements. For Tier 3, the only acceptable topologies are edge device or air-gapped on-premise with no hybrid routing. This is non-negotiable. Architecture that allows Tier 3 data to touch a path that could reach a cloud endpoint fails the basic diligence test. Print this classification scheme. Put it in your architecture review template. It will save you from the most common and costly mistake in enterprise AI deployment. And in the next chapter, we will take this framework and run the real numbers. Because knowing which topology to use is only valuable if you can also prove the total cost of ownership to your CFO. Let's start with what your Clouders pricing page actually means in practice. Because the number you see is never the number you pay. Cloud LLM billing breaks down into 3 components: input tokens, output tokens, and context window overhead. For GPT-4 today, that's roughly 5 per million input tokens and 15 per million output tokens. Sounds manageable until you do the enterprise math. A single document summarization workflow processing 10,000 documents per day, each averaging 2,000 input tokens and 500 output tokens, generates 20 billion input tokens and 5 million out tokens per month. That's 100 in input costs plus 75 in output costs, per month from one workflow alone. The formula is deceptively simple. Monthly cost equals open parenthesis input tokens times price plus output tokens times output price close parenthesis divided by 1 million. But the inputs to that formula, your actual token volumes, are almost never what you estimated in the proof of concept phase. And here is what most architects miss entirely. The input to output ratio is not fixed. RAG pipelines with large context injection can push input ratios to 10 to 1 or higher, completely invalidating your initial cost model. Before we move on, ask yourself, do you actually know your production input-output token ratio right now? Most teams don't, and that gap is where budget overruns are born. Now here is where the cloud economics story gets genuinely dangerous for enterprise planners. At low volume, say a pilot with a few hundred users, cloud API costs look almost trivially cheap. That's intentional. Vendors price aggressively at the low end because they know the switching cost increases dramatically once you're embedded. But watch what happens when you model growth. If your usage grows at 3 nms per year, a conservative estimate for a successful enterprise AI deployment, your cloud API bill doesn't grow linearly. It grows with a scale penalty. Why? Because higher usage means larger context windows as your retrieval systems mature, more complex chaining workflows, and higher output verbosity as users discover more powerful use cases. In practice, we observe that enterprises hit a usage inflection point around 50 million requests per month, where the per request cost, when you account for all overhead, actually increases rather than decreases. Contrast this with on-premises or private cloud infrastructure, where the cost approaches near zero once hardware is deployed. The timeline tells clearly, month 6, I love month 12, month 24, That's not a projection. Those are real figures from a mid-size financial services firm I worked with. The question is not whether this happens. The question is whether you've modeled it before signing the contract. Every cloud LLM architect knows the visible costs. Input tokens, output tokens, those appear on the invoice. What doesn't appear on the invoice are the hidden cost categories that can add 20 to 40% to your actual spend. Let me walk you through the ones that consistently blindside enterprise teams. First, retry cost. Language model APIs fail. Rate limits, timeout errors, context length violations. Production systems need retry logic, and every retry is a full duplicate token charge. In high availability deployments, retry overhead averages 8 to 12% of total token spend. Second, rate limit buffer provisioning. To avoid hitting rate limits, teams over-provision their request quotas. That buffer capacity costs money even when unused, and most enterprises maintain a 30% headroom buffer as standard SRE practice. Third, the latency tax. When your LLM API response takes 4 to 8 seconds, your application UX degrades. The business cost of that latency, measured in user abandonment rates, support tickets, and productivity loss, is real but invisible in the infrastructure budget. And fourth, observability spend. Logging every token in and out for compliance, debugging, and cost attribution requires a serious data pipeline. At enterprise scale, that monitoring infrastructure alone can cost $1,000 per month. Add these up before you approve that cloud AI budget, because your vendor's pricing calculator shows you exactly none of them. Next, we flip the model entirely and put real numbers on what local infrastructure actually costs to build and operate. Now let's put real numbers on the local LLM infrastructure side. The CapEx story starts with GPUs, and the numbers are significant, but they are finite, which is the critical strategic difference from cloud billing. An NVIDIA H100 SSM 80 gigabytes currently lists at approximately $2,300 per unit. A production-grade local LLM cluster capable of serving a 70 billion parameter model like Llama 3 at enterprise throughput requires a minimum of 4 H100s, putting your GPU hardware cost at $2,000 before you touch anything else. Add the server chassis at Dallo Wilson to Dallo Iwan Watson. High-speed NVLink or InfiniBand networking, NVMe storage array wave for KV cache at Dallo Balwashan, and a power distribution and cooling upgrade at Dallo Pylon to Dallo Manitson. Your total hardware capex lands between Dallo Paktili Samaman and Dallo Easy Sin for a serious single node cluster. Now, by standard ISET amortization, 3-year straight-line depreciation gives you a monthly hardware cost of Dallo Satam Pybret to Dallo Utun Kuvid. Compare that to a single month of enterprise cloud API spend at scale, and you start to see the structural advantage of fixed cost infrastructure. But CapEx is only half the story. The A100 is still viable for many workloads at Dallo to Dallo Maritun per unit, making a cost-optimized cluster accessible for under Dallo. And the hardware decision tree matters. And we'll use these figures directly in the break-even calculation coming up in 2 scenes. Capital expenditure gets the headline, but operational expenditure is where local LLM deployments quietly exceed their budgets. Let me quantify the 4 major OpEx components you must model before your CFO approves the hardware purchase. First, power and cooling. A 4H100 cluster at full inference load draws approximately 10 to 12 kilowatts continuously. At a US enterprise data center average of Dallo Yongchon Sen per kilowatt hour, that's Dallo Sidri Igi to Dallo Piling Wolf per month in electricity alone. Factor in cooling overhead at 1.4 PUE, and your true power costs around Dallo Sun to Dallo Chun EBIT per month. Second, and this is the number most architects underestimate, MLOps engineering staffing. Running local LLMs in production requires dedicated expertise, model quantization management, VLLM or TGI serving infrastructure tuning, GPU driver and CUDA compatibility management, and incident response. Industry surveys consistently show 0.5 to 1.0 FTE here ML engineering time per GPU cluster. $80 per annual fully loaded cost. That's $2 per month in staffing, your single largest OpEx line item. Third, model update cadence. The open source LLM landscape moves fast. Evaluating, fine-tuning, and deploying new model versions requires 20 to 40 hours of engineering time per major update cycle, typically quarterly. Fourth, software licensing, VLLM enterprise support, monitoring tools, and security scanning add $1 to $100 per month. Total monthly OpEx, $100 to $100. This is not a deterrent, it is a calibration. The question is always relative to cloud spend, and that comparison is exactly what we tackle next. Now we can do the calculation that this entire chapter has been building toward, the break-even point. This is the monthly request volume at which local LLM and infrastructure becomes cheaper than equivalent cloud API spend. And it is the single most important number in your enterprise LLM business case. Let's use a concrete work scenario. Assume a GPT-4 class workload. Average 1,500 in tokens and 400 output tokens per request. Cloud cost per request, 1,500 divided by 1 million times $5 plus Pearsona divided by 1 million times $spool equals $0.25 per request, roughly 1.35 cents. Add 35% for hidden costs we identified earlier. Effective cloud cost is $2 per request. Local infrastructure total cost, $178 capex amortization plus $100 opex equals $578 per month fixed cost. Monthly requests to break even. $78 divided by equals approximately 77,000 requests per month. Call it 1 million requests. Below 1 million monthly requests, cloud wins on pure cost. Above 1 million, local infrastructure wins, and the gap widens dramatically with scale. For reference, 1 million requests per month is roughly 33,000 per day, or 23 per minute. A medium-sized enterprise document processing pipeline, not a hyperscale system. Many enterprises cross this threshold within 6 months of production deployment. And critically, this calculation does not yet account for compliance cost adjustment, which we will cover in the final section, and which can move this break-even point by a factor of 3 in regulated industries. The numbers are clear. The decision, however, requires 4 more axes beyond cost alone. Everything we've calculated so far assumes a clean, unregulated environment. For most enterprise architects in this audience, financial services, healthcare, public sector, manufacturing with export controls, that assumption is dead on arrival. Compliance cost is not a soft consideration. It is a hard financial variable that must be added to every cloud TCO calculation. Let me show you how dramatically it shifts the numbers. Under Korea's Personal Information Protection Act, or equivalent GDPR in Europe, A data breach involving personal information processed through a third-party cloud API trigger fines of up to 3% of global annual revenue. For a mid-size financial institution with talo 500 million annual revenue, that's a talo 10 million maximum exposure per incident. Risk-adjusted, even at a 1% annual breach probability, which is conservative given recent cloud-vowed vendor incidents. That's talo 150 in annualized expected fine cost alone. Add to this, mandatory cloud security assessment overhead at talo 30 palpai annually under Korea's Financial Security Institute guidelines, contract compliance review at talo 20 and continuous audit trail infrastructure at talo 30 per month, as we already modeled. The compliance-adjusted cloud TCO for a regulated enterprise looks fundamentally different from the raw API pricing. In the worst case, compliance cost adjustments move the break-even point from 1 million monthly requests down to 3,000 monthly requests, a threshold that some teams cross in the first week of production. The implication is stark. For regulated enterprises, the default assumption should be local first, with cloud as the exception requiring specific justification. But regulations are not the final word. There is one more lens we need to apply. Let's bring everything together into a single decision-ready TCO model that you can take directly to your CTO or CFO. Across this chapter, we have built a complete 4-axis cost picture: the visible cloud API costs, the hidden cloud overhead, the local infrastructure CapEx and OpEx, and the compliance adjustment layer. When you combine all of these into a single comparison table, a clear pattern emerges. At low volume, under 300,000 monthly requests in a compliant environment, Cloud API is the rational choice. There is no capital commitment, no staffing requirement, and the risk is proportionate to the spend. Between 300,000 and 1 million monthly requests, the decision becomes context-dependent. Regulated industries should lean local, unregulated can stay cloud, with active cost governance. Above 1 million monthly requests. And this is the zone where most successful enterprise deployments land within 18 months. Local infrastructure is structurally cheaper, more controllable, and increasingly the architecture of choice among sophisticated enterprise buyers. The 4 keywords to anchor this model in your memory: volume, regulation, staffing readiness, and vendor dependency. These are the 4 axes of the enterprise LLM decision framework. And in the next chapter, we will give each axis a scoring rubric so you can produce a defensible audit for any stakeholder in your organization. The math is done. Now let's build the framework. In the previous chapter, we broke down the real TCO numbers: hardware amortization, GPU depreciation, engineering overhead. But raw numbers don't drive decisions. Scores do. The first axis of our 4-axis framework converts that TCO analysis into a single integer from 1 to 5. Here is how the rubric works. A score of 1 means cloud is dramatically cheaper. Typically when your workload is under 50,000 tokens per day, and you have no dedicated ML engineers. A score of 3 means parity, the classic 18 to 24-month crossover point we identified in the TCO model. A score of 5 means local wins decisively, high volume, predictable workloads above 1 million tokens per day, where GPU amortization fully absorbs operational cost. The critical discipline here is that you weight this axis before you calculate it. Cognitive bias always inflates the cost of whatever option you haven't tried yet. Lock in your weights first, then run the numbers. But here is what most architects miss about the TCO axis. Cost alone has never killed a cloud AI project. The governance axis almost always fires first. The second axis, data governance, is where most enterprise AI projects either earn their license to operate or get shut down by the CISO. The governance axis is built on a 4-tier data classification model that your organization almost certainly already has. You just haven't mapped it to LLM data flows yet. Tier 1 is public data: marketing copy, product documentation, anything already published externally. Cloud processing is fully acceptable. Tier 2 is internal data, internal wikis, non-personal operational metrics, anonymized logs. Cloud processing is acceptable with contractual DPA controls. Tier 3 is confidential data, employee PIDL, customer behavioral profiles, financial projections. This is where GDPR Article 28 and Korea's PIPA Article 26 processor agreements become mandatory gates, and where cloud vendors' standard agreements frequently fall short. Tier 4 is restricted data: medical records under HIPAA, payment card data under PCI DSCS, classified government data. Cloud processing is a compliance violation by default. Governance axis score is simply the highest data tier that your LLM workload will touch. If even one prompt contains tier 4 data, your governance score is 5, and local deployment is not optional, it is mandatory. But classifying the data is only half the battle. You still need to prove where that data actually flows. Knowing your data classification tier is not enough, you need evidence. Regulators and internal auditors will ask one question: can you prove it? This checklist operationalizes the governance axis by tracing data residency across 3 dimensions: origin, transit, and storage. For origin, document every upstream system that feeds your LLM. Is it a CRM containing personal data? A financial ledger? Each upstream system inherits the sensitivity of its most restricted data element. For transit, is the data encrypted in motion with TLS 1.3 or higher? Does the transmission cross a national border? Because if it does, cross-border transfer rules under PIPA Article 28.8 and GDPR Chapter 5 apply immediately. Storage. Does the LLM provider retain prompt data for model training? Most standard cloud API agreements include a training opt-out, but it requires explicit configuration. The default is often opt-in. This checklist produces a binary gate. If any item is flagged as a warning, your governance axis score automatically elevates to the next tier. There is no partial credit in compliance. Now that we have axis 1 and 2 scored, the regulatory compliance axis, axis 3, introduces something even more powerful: hard legal gates that override your weighted matrix entirely. Axis 3 is where the framework gets teeth. Regulatory compliance is not a weighted score. Certain regulations function as absolute gates. If you fail a mandatory compliance check, no amount of cost savings or operational convenience can override it. The questionnaire works in 2 passes. The first pass identifies your regulatory universe. Are you subject to PIPA, Korea's Personal Information Protection Act? Are you a financial institution under FSSAI Guideline 2023? Do you handle medical data under HIPAA or payment data under PCI DSS? Each applicable regulation adds to your compliance burden. The second pass maps each regulation to specific LLM data flow requirements. Under PIPA Article 28.2's, automated processing that significantly affects individuals requires human review capability, which means your LLM inference pipeline must have an explainability or override layer. Under FSSAI guidelines, financial institutions must maintain model version traceability and audit logs for a minimum of 5 years, a requirement that cloud LLM APIs with black box versioning structurally cannot meet. Under PCI DSS requirement 12.8, third-party service providers, including cloud AI APIs, must be formally assessed in your vendor risk program. Each failed gate produces a compliance axis score of 5, a hard recommendation for local deployment regardless of cost. But even if you clear all regulatory gates, you still face the most underestimated axis of all: your own team's operational capacity. Axis 4, operational complexity, is the axis that honest architects hate to score, because it requires the most brutal self-assessment. Every local LLM deployment I have reviewed that failed in production had the same root cause: the organization overestimated its own MLOps maturity. The operational complexity axis measures 5 dimensions. First, infrastructure management capability. Does your team have GPU cluster administration experience, or are they purely software engineers? Second, MLOps tooling maturity. Do you have a model registry, experiment tracking, and a CI/CD pipeline for model updates? Or are you planning to manually copy model weights between servers? Third, model lifecycle management. Who owns model version decisions, and what is your rollback procedure when a model update degrades production quality? Fourth, on-call and incident response. Do you have 24/7 on-call coverage for inference infrastructure, or will a GPU driver crash at 2 a.m. become a P1 incident with no owner? Fifth, security operations. Can your SecOps team handle GPU firmware vulnerabilities and container runtime CVEs on the same timeline as application vulnerabilities? Score each dimension from 1 to 5. Average the 5 scores. An organization scoring below 2.5 on operational complexity should not deploy local LLMs without a managed service layer, regardless of what the cost axis says. Now let us see what happens when you combine all 4 axes. Now we assemble the final decision matrix. The 4 axes are weighted as follows: TCO at 30%, data governance at 30%, regulatory compliance at 30%, and operational complexity at 50%. Notice that compliance and governance together account for 60% of the total weight. This is intentional. In enterprise architecture, cost optimization is a goal, but regulatory violation is an existential event. Let me show you 3 organizational profiles. Profile A is a Korean financial institution. High token volume giving a TCO score of 4, Tier 3 customer data giving a governance score of 4, FSS and PIPA requirements giving a compliance score of 5, and a mature DevOps team with a moderate MLOps gap giving a complexity score of 3. Weighted total, 4.5 out of 5. Recommendation: local LLM deployment with managed inference infrastructure. Profile B is a Series B startup. Low token volume giving a TCO score of 2, internal data only giving a governance score of 2, minimal regulatory burden giving a compliance of 2, and a small engineering team giving a complexity score of 2. Weighted total, 2.0 out of 5. Recommendation, Cloud LLM with DPA controls. Profile C is a public hospital. Medium volume TCO score of 3, medical records governance score of 5, HIPAA Hardgate giving a compliance score of 5, and a developing IT team giving a complexity score of 2. Weighted total, 4.1 out of 5. Recommendation, local LLM, but with a managed service overlay to compensate for operational immaturity. The matrix does not make the decision for you. It forces you to document why you chose what you chose. And that brings us to the most important artifact in enterprise governance. The architecture decision record. A decision without documentation is not a decision, it is an opinion. In enterprise architecture governance, the architecture decision record, or ADR, is the canonical artifact that transforms a weighted matrix score into a defensible, auditable, and reversible architectural commitment. The ADR format was originally codified by Michael Nygaard in 2011 and has since been adopted across ISO 42000 architecture description standards and TOGAF ADM Phase E deliverables. For LLM architecture decisions specifically, the ADR serves three critical governance functions. First, it creates an audit trail that regulators, auditors, and board-level risk committees can follow, showing not just what you decided, but what alternatives you considered and what risks you accepted. Second, it creates a trigger mechanism. The ADR specifies what conditions this decision should be revisited, preventing architectural debt from silently accumulating when your regulatory environment or cost structure changes. Third, it distributes institutional knowledge, because the single most dangerous event in any AI infrastructure program is the departure of the one person who remembers why you made the original architecture call. The ADR is structured around 5 mandatory sections: context, decision, consequences, alternatives considered, and review triggers. Let us build one together using the financial institution profile from our decision matrix. Let us populate the ADR using the financial institution profile. The context section answers one question: what problem forced this decision? For our bank, the existing Cloud LLM API integration transmits customer financial query data to a US-based provider, creating PIPA Article 22 to heat cross-border transfer exposure, and an FSS AI guideline model version traceability gap that a Q3 audit identified as a high-severity finding. The decision section states the chosen architecture precisely. Deploy a local LLM cluster using 2 NVIDIA A110 GB nodes running a fine-tuned Llama 3 via isolated within the existing on-premises data center network segment, with all inference traffic remaining within the Korean jurisdiction. The alternatives considered section is where most architects cut corners, and where auditors focus first. You must document at least 3 alternatives. Continue with Cloud API under Enhanced DPA, deploy Cloud LLM in a Korean region sovereign cloud offering, or adopt a hybrid architecture with data anonymization pre-processing. For each alternative, document why it was rejected with the specific evidence, not opinion. The consequences section lists both positive outcomes and accepted risks. Positive, PIPA compliance restored, FSS audit finding remediated, projected 30% to 3-year TCO reduction at current token volume. Accepted risks, 14-week deployment timeline, GPU hardware single vendor dependency on NVIDIA, team MLOps upskilling required within 6 months. Every risk in the consequences must have a named mitigation owner. A risk without an owner is not a risk, it is a future incident report. An ADR that sits in a document repository and is never reviewed again is governance theater. The final step is integrating the LLM ADR into a living architecture governance workflow with automated review triggers. There are 4 categories of trigger events that must force an ADR review cycle. First, model version changes. Any change to the foundation model, including minor version updates, triggers a review of the consequences section, because capability changes in the model may alter your data processing profile or compliance posture. Second, regulatory updates. New PIPA enforcement guidance, FSS circular updates, or GDPR adequacy decision changes must trigger a compliance axis rescore within 30 days of publication. Third, cost structure changes. If your cloud provider changes API pricing by more than 20%, or if your GPU hardware maintenance costs exceed the original TCO model projections by more than 50%, the TCO axis must be recalculated. Fourth, organizational capability changes. If your MLOps team composition changes significantly through hiring, restructuring, or key person departure, the operational complexity axis must be rescored. The ADR should be stored in the same version control system as your infrastructure code, not in a SharePoint folder with a date in the file name. Tag each ADR version against the model version and regulatory snapshot it was reviewed against. This chapter has given you a complete 4-axis decision framework and the governance documentation structure to implement it. In the final chapter, we will move from framework to action, identifying the 3 most common implementation pitfalls, giving you your specific next architecture move based on where your organization scores today. Let's talk about the mistake that kills LLM projects before they ever reach production. Enterprises approve the budget, the architecture looks clean on the whiteboard, and then reality hits. GPU procurement lead time is 16 to 20 weeks for H100 class hardware. Power infrastructure upgrades to support 10 to 30 kilowatts per rack require facilities work that no one budgeted for. Cooling redesigns add another 3 to 6 months. By the time the hardware arrives, the business requirement has shifted, and now you have expensive iron with no approved use case. NIST 830 to 37 management frameworks require capacity planning as a formal gate, yet most local LLM pilots skip this entirely. The financial sector equivalent is acquiring a trading system without provisioning the network latency budget. Hardware underestimation is not a technical failure, it is a governance failure. And here is the dangerous part. The second mistake is invisible until your model starts silently giving wrong answers in production. The second mistake is more insidious because it looks like a success story. The enterprise moves off the cloud API, data sovereignty is achieved, the compliance team signs off, and then, 6 months later, the model is quietly drifting. No one updated the weights. No one is monitoring output distribution. No one built a drift detection pipeline because, quote, we own the model now, so we're safe. This is the model governance gap, and it is how local LLM deployments create shadow AI, the very risk profile they were designed to eliminate. In the financial sector, Korea's FSS electronic finance provision guidelines require ongoing model validation. In healthcare, model output audit trails are a regulatory requirement. A local model with no update cadence, no A/B testing framework, and no anomaly detection on inference outputs is not safer than cloud AI. It is less safe, because at least cloud APIs push updates. The correct posture is to treat local LLM exactly like any production ML system, version-controlled, monitored, and subject to formal change management. But wait, even if you solve hardware and governance, there is still a strategic mistake most architects make about the shape of the architecture itself. The third mistake is architectural, treating the cloud versus local decision as binaries. It is not. The mature enterprise pattern is sensitivity-based routing, a hybrid architecture where a classification layer inspects every inference request and routes it based on data sensitivity, latency requirements, and cost tolerance. PA-bearing prompts, regulated financial data, and internal IP go to the local LLM cluster. General purpose, non-sensitive, and high-complexity requests that require frontier model capability are routed to the cloud API. This is not a compromise, it is optimal design. It gives you data sovereignty where regulation demands it, frontier model quality where it delivers value, and cost efficiency by reserving expensive GPU compute for sensitive workloads only. The routing layer itself is a 10 to 50-line policy engine, not a complex system. Organizations like Kakao Bank and major Korean insurers are already running this pattern in production. The false binary, all cloud or all local, is how architects create either vendor lock-in or operational debt. The right question was never which one, but which workload goes where. With that, we have mapped all 3 pitfalls. Now let us pull the entire architecture together into a single visual structure you can take into your next architecture review. Let us now do what every good architecture review demands at its close. Synthesize. Across 6 chapters, we have built a coherent decision system. It starts with the risk taxonomy, vendor lock-in, data exposure, cost volatility, and maps onto the 3 runtime deployment patterns, cloud API, local open weight, and hybrid. We then quantified the risks through the TCO model, separating cloud OpEx curves from local CapEx amortization. The 4-axis framework, total cost of ownership, data governance, regulatory compliance, and operational complexity, gave us the scoring instrument. And the output of that scoring is the architecture decision record. The ADR, a formal artifact that makes your reasoning auditable, reversible, and communicable to stakeholders. You are looking at now is not just a lecture summary. It is a decision-making scaffold you can instantiate for any AI workload in your organization. Notice how each node connects. Risk drives axis selection, axis scoring drives ADR content drives infrastructure procurement. This is the closed loop of mature AI governance. And here is the question you should be asking right now. Which of my current AI workloads has never had an ADR written for it? This framework does not exist in isolation. It is the entry point to a broader capability map you will need to build. The first adjacent domain is RAG architecture design, retrieval augmented generation. Once you have decided where your LLM runs, the next question is what knowledge it can access. RAG architecture determines how your local model connects to enterprise document stores, vector databases, and real-time data feeds without retraining. The second domain is fine-tuning strategy. Open-weight models like Llama 3 or Mistral can be domain-adapted using LoRA or Kikilora techniques with as little as 10 gigabytes of GPU memory. But fine-tuning without a data governance policy is how you accidentally bake PIA into model weights. The third domain is MLOps pipeline construction, the operational backbone that handles model versioning, B testing, canary deployments, and the drift detection we identified as the governance gap. Each of these topics is a full lecture in itself, but they are all downstream of the decision you have just learned to make. You cannot design a good RAG pipeline if you have not decided where inference lives. You cannot build a fine-tuning strategy without a TCO model that accounts for training compute. The framework is the foundation, and the foundation is now yours. Theory without action is just documentation. So here is your concrete 30-day mandate. In the first week, identify one existing AI workload in your organization, ideally one already using a cloud API, and run the 4-axis scoring exercise on it. Score TCO, data governance, regulatory compliance, and operational complexity on a 1 to 5 scale for both cloud and local deployment. In week 2, draft the architecture decision record for that workload. Use the ADR template from this lecture. Context, decision drivers, options considered, decision made, consequences, and the reversibility clause. In week 3, identify your pilot deployment candidate. The ideal pilot has moderate sensitivity, a defined query volume, and an existing team with Python or Docker familiarity. In week 4, present the ADR to your architecture review board. The goal is not to get approval for a full deployment. It is to establish the governance habit of writing ADRs for AI workload load decisions. This is how architectural maturity compounds. Every organization that has successfully navigated the cloud-to-local transition started with exactly this. 1 scored workload, 1 written ADR, 1 pilot candidate. The enterprises that are still trapped in cloud vendor lock-in 2 years from now are the ones that kept waiting for the perfect moment to start. That moment is the next 30 days. The framework is in your hands. Now use it.